Okay, so in this lecture, we're going to be talking about uncountably infinite sets. So before you watch this, of course, make sure you do the reading. So section 3 of chapter 22 of Logic and Proof and section 16 of Fundamentals of Higher Mathematics. Okay, so the first definition is just to say what uncountable means. So we say that if a set is not countable, that is, if it's not finite or countably infinite, we call it uncountable. And of course, since all of these sets are not finite, they're uncountably infinite, you could say. So all uncountable sets are infinite. Our first theorem tells us what our favorite uncountable set is, which is the real numbers. So the real numbers are going to be the most familiar uncountable set. So we saw in the last lecture that the natural numbers, the integers, the rational numbers, those are all countable, sometimes surprisingly, especially I think for the rational numbers. And now finally we find a set that isn't actually countable, that isn't in bijection with the natural numbers, and that's the real numbers. Okay, so for the proof, we're going to suppose that it's not the case that R is uncountable, which is to say that R is countable. And we know, at least from the book, I didn't say it so explicitly in the lecture, but we know that if a set is countable, then there is a surjection from the natural numbers to our set, and in this case it's R. So there has to be a surjection from S to R. Okay, so now the proof proceeds with kind of a trick. So we're just going to do it, just going to write out the proof first and then go back and try to develop some intuition about the proof strategy. Okay, so what we're going to do is we're going to give names, first of all, to all of the digits of all of the real numbers in the image of S after the decimal points. So we're going to let S sub I to the j denote the ith digit of S of j after the decimal point. So to be clear, let's look at the real number S of 0. That's going to be something point S00, S10, S20, S30, dot, dot, dot. So we're giving names to all of the digits after the decimal point in S0. Okay, so now we're going to construct a new real number. So for each natural number n, we're going to let R sub I be a natural number which is between 0 and 9, so it's a digit like all the Sij's, and such that Ri is not equal to Sii. So we want to come up with R5, let's say. So we look at S55, so the fifth digit after the decimal point of S of 5, and say that guy is 7. Then we choose something different for R sub 5, so let's say we choose 9 for R sub 5, then that would be good. Okay, then we let R equal the real number that we get by putting all of these guys together into a real number, which we can more precisely or rigorously define as an infinite sum, like this. And this is a real number, which by construction is not in the image of S. But this is a contradiction because we said that S was a surjection, right? So that contradicts what's going on. So our initial supposition, our initial hypothesis that R is actually countable is not the case. So we conclude that R is uncountable. So this is a contradiction. And now let's review what just happened and think about it a bit more. So we have all these real numbers. So since we're supposing in the proof that R is countable, we can count through them or make a sequence, a list of all the real numbers. And we've decided to give parts of these real numbers names. We don't care about what's in front of the decimal point. We really care about what's after the decimal point. So we look at S of 0, and as we said, that looked like S00, S10, S20, S30, S40, etc., etc. And so S of 1 is the same. So we have S10, S11, S12, S13, and this guy looks like this, and this guy looks like this. Okay, so we have kind of a grid of all of these. So going down, we have all the real numbers, and going across, we have all the digits of the real numbers. And what we've done is we've come up with a new real number that we want to not be in the list. So it's not in this list, this infinitely long list of real numbers. That's our goal. So we do that by saying, okay, we don't care about what's in front of the decimal point, but we can engineer this number to be different than the other ones by looking here at all these guys whose subscript and superscript are the same. So this is the diagonal. And we say, okay, let's just choose R0 to be something different than S00. And by doing that, we'll make sure that R is not equal to S of 0, because they might agree, some of the digits might agree, but by design, R of 0 and S00 do not agree. So the first digit after the decimal point does not agree. So these two numbers are not the same. And similarly, we choose R1, so that is any digit that's not S11. So these two digits, S11 and R1, do not agree. So S of 1 and R cannot be the same. And we choose R2 so that it's a different digit than S22. And then since the third digit after the decimal point, those two guys are different in S of 2 and in R, these two numbers have to be different. And then we choose R of 3 so that it differs from S33, and so on and so forth. And so in this way, we construct a new real number that's different than any of the real numbers in our list. So we can imagine that we just do this process infinitely many times, countably many times, and then we get a different real number than any of the real numbers in our list. So I want to say that this is what's called a diagonalization argument. And the idea is that there is enough space somehow, in some sense, in a real number. So in our real number R that we want to make sure is different than all of the S's, there's enough space, there's enough information that can be stored in R to make sure that it's different from countably many other real numbers. So since there are countably many digits that occur in any real number after the decimal point, that's like enough to make sure that R is different from countably many real numbers that we already have. So we have just as much space kind of information in the real number R as we have real numbers S of 0, S of 1 that we want to make sure are not the same as R. Okay, so that's the idea. All right, so now for the rest of this lecture, I'm going to be talking a bit about computer programs, kind of loosely, because I don't want to spend too much time getting in the weeds of how to define all this stuff. But this gets really interesting when we start thinking about it in terms of computer programs. So let's define first, very, very roughly, what a computer program is. So we're going to fix a finite, non-empty set of elements, or set of characters, let's say. Set of characters sigma. So for any computer program, you always have a set of characters that you can use. So say Unicode, or more frequently in the real world, you can use characters from ASCII. So these are just the characters that you can type on your keyboard, for example. And then we're going to let sigma star denote the set of all strings with characters from sigma. So all of the things that we can type on our keyboard, you can think of this. So sigma star is all the things we can type, all the programs that we can write on our computers. So to be very precise, we talked a little bit before, as mentioned a bit before in this class, not very strongly, that strings are the same as tuples. And now we're allowing any length of string, so it could be 2 characters long, it could be 1,000,000 characters long. So we're going to define sigma star to be the union of all of the sigma to the I. So sigma to the 5 is sigma times sigma times sigma times sigma times sigma, which we've talked about before. And we want to take a big union of these sets for all the natural numbers, so from 0 to infinity. So we want to take the union of sigma I for every natural number I. Okay, so a computer program, and I'm being a bit loose with this definition, and but what I'm thinking of in the back of my mind is called a Turing machine. So this is a abstraction that people use to think about computer programs. So a computer program, we can say, is a string P written in our set of characters, sigma, which defines a partial function, let's call it bracket P from sigma star n to sigma star for some n. Okay, so let's think about what's going on here. Let me say a bit more about these words. So we're defining a computer program to be, first of all, a string. So we're thinking of this as literally being the computer program that you write in Python or whatever, so a bunch of characters that make up the computer program. And we can forget about all the graphical user interfaces and stuff like that, and just think about a computer program as something which takes in some input, maybe from the user, and then does something to that input and returns an output. So this domain here is the input, so it can take 0 pieces of input, That would be when n is 0. It could take 2 pieces of input. That's when n is 2. So it can take any number of inputs. And it will just then, after it runs, it will give you some answer, some information, some output. But I've used this word partial, which we haven't talked about before. So we have to say that a computer program is a partial function because sometimes, I mean, we try to avoid this if we're good programmers, but sometimes you write a computer program and you give it some input, and the computer program will never terminate. It will loop forever. It will never stop running and give you an answer. It will just keep going and never return anything. And so we can kind of capture this behavior with the notion of a partial function, which is a kind of like a function, but not every input has an output. So with a function, say from x to y, every element of x has to go to an element of y. But with a partial function, only some elements of x go to elements of y, and for other elements of x, if you ask the function where it goes, it's just undefined, it doesn't go anywhere. So a partial function is like a regular function, but for some guys in the domain, for some inputs, the function doesn't have anywhere to put the input, doesn't have any information that corresponds to that input. Okay, so let's think about what's going on here a little bit in terms of cardinality. So the first thing to say is that sigma star is countably infinite. And I won't prove this. I think that it's very instructive to think about this yourself. But each one of these constituent sets, sigma to the I, is finite. And then when we take the union of them, we're going to get infinitely many programs that we can write. So infinitely many possible programs, and also infinitely many pieces of input that we can give a computer program. Okay, so now the interesting result of this is that there are infinitely many, uncountably many actually. Let's try that again. Infinitely many or uncountably many real numbers that cannot be printed or, let's say, returned by a computer program. So this might be surprising. You think you can certainly write a computer program that, given some input, could produce any real number. Given the right input, it could produce any given real number. But this is not true. There are many real numbers that just cannot ever be printed by any computer program on any input. And I think this is a really surprising result, and it just comes down to cardinality. There are just many, many more real numbers than programs. So the sketch is the following. The set of possible combinations of computer programs and inputs is sigma star for the set of computer programs times sigma star for the set of inputs. And now I'm really just considering programs that take one string as an input, but this is easily generalizable to programs that take more strings as input. So we see that the set of pairs of computer program and input is sigma star times sigma star, because sigma star is both sets of computer programs and inputs. And we saw in the last lecture that this is countably infinite, because sigma star is countably infinite. But we also saw in the last lecture, or sorry, in this lecture, that the set of real numbers is uncountable. which means that there are many, many more real numbers than pairs of computer programs and inputs. So there's just no way to print every real number. It's not possible. Okay, so that's the first surprising result. And the second, maybe not surprising result because I think it is now baked into our understanding of computer programs, but it's one of the first major results regarding computers, is the halting problem. It's usually called. And I want to make a note that this was proven by Turing in 1936, so that was way before there were actual computers. So he invented the notion of Turing machine before anyone else had made an actual computer, and used that formalism to prove results like this and to understand, way before there were computers, what a computer could be. Okay, so the statement of the halting problem is the following. So a lot of people wondered if there was a way to basically decide any problem, to come up with an answer to any problem. And he showed that at least there's no computer program that can decide or can determine whether any computer program will, one, finish running. So in that case, we say that the computer program halts, or two, run forever. So if this were possible, I won't get into what's going on here in terms of other mathematical problems, but if this were possible, if it were possible to have such a computer problem or computer program, you could use it to solve many, many mathematical problems and other problems in other disciplines that are currently unsolvable. Okay, so Turing showed that this was not possible with a computer program. And the proof uses a diagonalization argument. So we want to first suppose that there is such a program. So we're supposing that the theorem or the statement of the theorem is false. So we want to suppose there is a program, and we're going to call it capital H for halting. And it's going to take two inputs and return, as usual, one output. And it's going to take in two strings, and it's going to think of the first string as being a description of a computer program. And it's going to think of the second string as being an input for that computer program. And it's going to return 1 if the program is good, if it finishes running on input I. So if P finishes running on input I, and it's going to return 0 otherwise, so if it just loops forever. Okay, so we're going to suppose we have such a, now what we understand to be a magical computer program which can tell us really anything we want. And we're going to use this as a tool to come up with a contradiction. So if we had such a computer program that gave us such profound knowledge, then we could define, so we can define a new program, let's call it N for new, from sigma star to sigma star defined by the following. So again, this is, well, something between a proof and a proof sketch. So we're going to say that N on some input P, which we're thinking of as a computer program, that's why I called it P, is going to be it's going to return something different. So this is a diagonalization argument, which we'll kind of see at the end when it's all wrapped up what has happened. So the diagonalization argument, so just as before, when we were choosing those Ri's, the R0, R1, we're just saying let R0 be something different than S0, 0. So again, here we're going to let N of P be something different. I don't know why I wrote otherwise, let's just write other. Something other than P of P if P of P does halt. So, i.e. if H of P equals 1, so this is where we're using H. H is telling us if P of P halts. And it's going to return something, let's say, 0 otherwise. So if P of P does not halt, then it's going to return 0, which is still different than P of P, right? Because P of P doesn't halt, but N of P does halt, and it returns 0. So it does finish computing, and it's going to give us the answer 0. So in both of these cases, N of P is acting different than P of P. So i.e. if H of P equals 0. That's the otherwise case. But then the program N, so remember N is a program taking input P, so just as a program, N is different from every program P from sigma star to sigma star by design, because it differs from P at the input P, which is kind of weird and paradoxical. But if we feed P to P, we get something different than when we feed P to N by design, because we just chose what N does at P by saying that it's different than what P does at P. And this is a contradiction because N is itself a program from sigma star to sigma star, so it can't be different from every program from sigma star to sigma star, because then it would be different from itself, which of course doesn't make any sense. So this is a contradiction, and so we can say that our initial assumption that there is such a program H that solves the halting problem that gave us enough knowledge to produce the program N gives us a contradiction. So that can't be, that can't exist. So let's look at a picture. So let's think about all the programs. So the programs, as I said, the programs are countably infinite. So the programs, we definitely know, this is not in question because we proved it. The programs can be enumerated, they can be counted out, because there are just as many programs as there are natural numbers. So we can have P1, P2, P3, P4, dot, dot, dot. And we can ask, so just as before we were looking at real numbers and we were looking at the digits of real numbers. Now in the columns we're not going to have digits because computer programs don't have digits, but we're going to ask what each program does to each, maybe I'll have slightly less guys here, so it's not so crazy. We can ask what each program does to each input, which we're still calling P1, P2, P3. So we're just enumerating the elements of sigma star, which is definitely possible. That's not under question. Okay, so let's just make up something. So let's say that if we run P1 with input P1, we get 0. If we run P1 with input P2, we get 1. If we run P3 or P1 with P3, let's say that it doesn't halt, it loops forever. So let's write a little infinity there to symbolize that. And so I'm just making these values up. So let's say this is how these programs behave on this input. So if we run P3 on input P2, it doesn't halt. Now we constructed n. So n is not in this list, at least by design. We want to say that n is definitely not in this list. And we do that by cooking up a computer program that returns something different on all of these inputs than what all of the PIs return. So we, by design, make sure that n returns something different if we feed it P1 than P1 itself does. Okay, so by design, what that is well, it should return something other than 0. So let's say that we've chosen 1 for it to return. And now if we feed n P2, we want it to return something and not infinitely loop, and we said explicitly what that was, which was 0. So we give it 0 there. And we want n, if we feed it input P3, to return something other than 0, because we want it to be different than the behavior of the program P3 when we feed it input P3. So let's say that guy is 1. So we've cooked up our computer program n to do something at input PI that's different than what the program PI does at input PI. So then n can't be any of these programs. And now the contradiction or what we are contradicting is slightly different than the diagonalization that we saw in the case of real numbers, because in that case we saw that the supposition that real numbers are countable was wrong. That was the thing that we contradicted. But now in this case, we know already it's not in question that these programs are countable. They are definitely countable. Sigma star is definitely a countable set. What we are contradicting is our assumption that we have this piece of knowledge, this program H, that gives us all this information by which we can, or with which we can construct n. So we are saying that this tool H cannot exist, or else we would reach this contradiction.